it's recorded. And so, Gaetan, ready to go?
So, thank you very much to the organizers for the invitation. It's the first time I'm in Oslo. So this talk will be some introduction to topological recursion from the point of view of the algebraic structures that are underlying it. So there will be not really new results, but rather a review and trying to put things together, especially for people who never heard about it before. Okay. So I will try to describe how the structure that we call topological recursion can arise from a very simple problem in algebra. And then I will try to give some examples that actually come from geometry. So there will be 2D TQFTs, intersection theory on a moduli space of curves. I will try to explain also, which was in fact historically the origin of topological recursion. How does it come up in matrix models? And at the very end, I will explain how this algebraic structure actually directly comes from geometry in certain cases. So I will introduce the notion of Airy structure, which was proposed by Kontsevich and Soibelman 3 years ago. So you take a vector space. I will always work over the complex field of complex numbers. And for simplicity, let's choose a basis of linear coordinates, xi. We want to consider the Weil algebra, that is the algebra of differential operators on that vector space. And it's convenient to add some some parameter h bar. So I'm going to look at differential operators. So that's polynomials in xi, h bar derivative dxi. There could be some extra powers of h bar with usual Leibniz commutation relations. You can make this a graded algebra by assigning to xi the degree 1 and h bar the degree 2. In that case, h bar derivative dxi, because h bar is degree 2 and derivative dxi is degree -1, that makes something of degree 1. So in the way I define my Weil algebra, all terms have monomials of non-negative degree. An Airy structure is going to be a linear map from the vector space V to the Weil algebra. So it's a collection of differential operators, one for each of the basis elements. And we want that this collection of operators satisfy two conditions. The first one is that up to terms of degree 2 and higher, you want Li, which is the image of the ith element of the basis, to start with h bar derivative dxi plus something. This means there's no constant term and there's no linear coordinate like xi. It's just a pure order 1 derivative plus higher order. And now these operators, you want them to form a compatible family in the following sense. If you commute 2 of them, it must be in the ideal generated, the left ideal generated by the Weil algebra of these various Li's. So I can write this condition by saying that when I look at the image of the vector space V by L, and I commute any 2 things from the image, I land up to a factor of h bar into something which is a combination, a linear combination of the L's that I already have, maybe multiplied to the left with coefficients that could be differential operators themselves. The main use of Airy structure is that once you have such a thing, there exists a unique formal function on the vector space V, because I'm talking about formal functions determined by its Taylor coefficient. So I'm going to write it as f equals sum of h bar to the g minus 1. That's the convention. And then the fgn as the Taylor coefficient. So there are symmetric and linear forms on V. And this function is such that its exponential of f is annihilated by all the operators I have in my Airy structure. And moreover, so there's existence, but also there's uniqueness, which happens when you normalize f01 and f02 to be 0. So this f, the leading order in h bar is 1 over h bar, and then it starts with a cubic term. And then you have higher order terms. So exponential of f will be called the partition function. And that's what we can get from an Airy structure. Okay, so I will not prove this theorem. It's not very hard. I will at least try to show you when Li has maximum degree 2 as terms, how the uniqueness is arising. So let's take Li, which is maximum terms of degree 2. So it must have this form with some scalars a, b, c, and d. And we're also going to decompose FGN, which is this n-linear form, on the basis of linear forms that we have, so the xi's. Now let's take Li and apply it to exponential of f. And then you remultiply by exponential minus f because you're going to act by derivative, so it's going to pull down something from f, and then remains the exponential you want to kill. And you want to solve that equation for any I, so you want to equate that to 0. So let's have a look at what happens for the term, for example, of h bar to the 0, and then which is quadratic in x. So if I want something like this, from the first term in Li, I need to, because I have f, which has an h bar to the g minus 1, and I apply h bar 0 dx. If I want an h bar to the 0, I need to take the g equals 0 term. And if I want something quadratic in the x's, because I'm eating one x with a derivative, I need to take something cubic in the x. So this is making appear this f03. Now let's look at the other terms. ai, xa, xb, that's indeed quadratic of order h bar to the 0. So it's just multiply exponential of f, it doesn't act on it. So this is there. And all the other terms are going to produce monomials that are not of this type. So your equation at this for this type of monomial is f03 equal aijk. So you could read at least one coefficient of the partition function from just knowing what the differential operator is. Now let's have a look at h bar times a constant. So I see that I can get that by acting with this first term h bar 0 dxi on f11, because f11 comes with an h bar to the 0 in the exponential. So that makes an h bar from the differential. And the 0 dxi is eating exactly the linear term. So that does produce f11. Then all the other terms, well, the a will get some x's, so it's not what we want here. The b also has some x, so we don't see it there. And for the c, well, the order in h bar is too big. That's related to the fact there is no f02 is 0. So that doesn't contribute either. The only thing that remains is this h bar times a constant, which is di. And this must be equal to 0, so f11 is equal to di. You can do that more systematically. So now you look at any monomial with some power h bar to the g and n-1 terms of type x, and you just collect coefficients. You're going to see from the first term in Li the fgn, and then a collection of other terms. A, we already identified it in a previous monomial, so it's not going to appear here. But B, I have a differential that's pulling down some f, and I already have some x, so I don't need to put it back. So at the end, what it pulls down is some fgn minus 1. Then for the C term, you have a second order derivative. So here you have two types of things. Either you pull down some f from the exponential and then you differentiate it again, or you pull down the differential twice something from the exponential. And if you collect what are the good pairs of h bar and the monomials in X, you find that you see some terms fg minus 1 n plus 1 and a quadratic term here. And this must be equal to 0 again. So in practice, one doesn't remember this formula like this. But what one can notice, which makes it easy to know what actually this is that this has a geometric interpretation. Let's take sigma, which is a smooth oriented surface of genus G with n labeled boundaries. And I will denote P generically a pair of pens, so a sphere with 3 boundaries and also labeled boundaries. And you can notice that the terms that I wrote here that appear in this formula at the top, they're in bijection with a finite set consisting in embedded class of embedded pairs of pens inside the surface, such that the first boundary of the pair of pens is the first boundary of the surface. And when you remove the pair of pens, you obtain a surface which is stable in the sense that the Euler characteristic of any component is negative. In other words, you don't have disks, you don't have cylinders. And we consider those things up to diffeomorphisms. In that case, well, what counts, what determines a point here is just the topology of what remains. So I wrote the terms here. There is terms correspond to the B term, where when you remove the pair of pens, there's one interior curve, and what you see to the left, sigma to the right, sigma minus P, this is a surface of same genus, but one boundary less. But you also have the situation where the pairs of pens, so it must bound the first boundary of the surface, but then there could be 2 boundaries of the pair of pens that are interior to the surface. And in that case, when you remove the pair of pens, either you see something disconnected, that's the term to the right. In that case, the genus and the boundaries are shared. You have to divide them between the 2 components. Or you don't disconnect the surface, but you have to lose this handle. And this exactly corresponds to this thing that we saw here. So this is, you could say, just a bijection between a set of terms and some topological picture. It looks a bit artificial. But at least what we learn without computing too much from this is that this relation here, FGN equal this sum or B and C terms, this is a recursion on 2G minus 2 plus N that uniquely determines FGN. Because when you remove the Euler characteristic of a pair of pens is -1. So when you remove it, so if I say minus the Euler characteristic of the pair of pens is 1, when I remove the pair of pens, the Euler characteristic is additive, so I just decrease 2G minus 2 plus N. And because I have no disks and no cylinders, indeed, I do come at the end, I only see things which strictly decrease. So we somehow proved uniqueness of this partition function. If you were looking not at quadratic differential operators, which is possible, you will still get a similar scheme when you just compute what is Li of exponential of f. However, now you will have more terms, which are in bijection with embedded subsurfaces, sigma prime into sigma, which bound the first boundary of the surface, such that when you remove sigma prime, there's a word missing, sigma minus sigma prime is stable. So you just get not only pairs of pens that you remove, but here with 4 boundaries, with 5 boundaries, surfaces with some genus, etc. The argument which I say. So we have now this formula to compute FGN. It doesn't prove uniqueness. It doesn't prove existence. Sorry. The reason is that when you ask for a function and FGN are the Taylor coefficients, it's better that the Taylor coefficients are symmetric, otherwise it's not a function. So existence is exactly proving that this formula, which looks actually quite non-symmetric, because some of these first boundary is playing a different role than the rest. What you obtain recursively in this way is symmetric. If you can prove that, then you have proved as well existence, and you have actually a formula to compute it. So this is not totally obvious that this formula produces something symmetric, but this is a consequence of this condition of compatibility, which I wrote here, that when you commute two differential operators, it's in the ideal generated by this family of differential operators. Somehow this is some kind of holonomicity condition which is sufficient to ensure the existence of a common solution to all of these PDEs. In the quadratic case, the situation is a bit simpler because Li has maximum degree 2. So Li commutator Lj has maximal degree 2 because the commutator between xi and h bar divided dxi just, this has degree 4, Li commutator Lj. And on the right, you want a priori the ideal condition tell you that you have a linear combination like that where f has differential operators. But since h bar is degree 2 and La is already degree 2, the only possibility is that Fij is degree 0. So this is a scalar. In other words, in a quadratic case, this ideal condition means that you have a Lie, this family of operators form a Lie algebra. You can write down explicitly that the conditions it put on the coefficients A, B, C, D, this is some quadratic condition. So if you really do that, you find out that the structure constant of the Lie algebra are related to the antisymmetric part of B. And for the rest, you get quadratic relations which are overdetermined. So a priori, it's very non-trivial to exhibit an Airy structure, to find a solution operators satisfying Lie algebras like that. Okay. So because this is very non-trivial to find Airy structures, you need shortcuts, or you need reasons to believe this exists. And some of this theory was arrived way after we actually had examples of such things. So what Kontsevich and Soibelman did was reformulating the theory of topological recursion in this simple algebraic context. So the Airy structure that we know very often, I mean, there's a class of it that comes from cutting and gluing relations in two-dimensional geometry. Meaning that this G and N, which so far was a bit artificial, I mean, the interpretation in terms of genus and number of boundaries was a bit artificial. Actually, this is because the problem that you're interested in, it's a problem about counting surfaces, and the Airy structure express some of ways, I mean, relation that appear when you cut surfaces. There's another aspect of the theory from which you can produce Airy structures is from conformal field theory. I will not speak too much about it, but we will see some concrete example of such an Airy structure that could be obtained from CFT. And related to this, it can also be obtained, you can obtain Airy structures from branch cover of complex curves. So this is related to what's called spectral curves, which some people in random matrix theory know about. And finally, I can also mention that if you just say, okay, I take a nice Lie algebra, like a semi-simple Lie algebra, and I want to classify such Airy structure based on that particular Lie algebra, that problem was solved recently by purely Lie algebraic techniques by Hadash and Ruba. However, these Airy structures, most of the time, we don't really know what the geometric interpretation for it. So I will not dwell on that. So as I said, this G and N in applications very often have the meaning of genus and number of boundaries. And in that case, the FGNs are counting surfaces, and this can be understood in a very broad sense. It depends on the context. So to mention a few applications, topological recursion can compute generating series of maps, which are discretized surfaces that appear as Feynman diagrams for matrix integrals. You can also count branch cover of surfaces. You can do integrals over the moduli space of curves. So this is like averaging over all surfaces. You can also do that by surfaces that are mapped to some target space X. And this is morally what Gromov-Witten theory is about. This is some of the direct applications. And because of all the algebraic structure behind these theories, in fact, there's some other applications where you don't really see surfaces appearing, but sometimes FGN can be used to compute certain things in knot theory, so in conformal field theory, in integrable systems, etc. So what I will do now is give some concrete example of Airy structures. And let's start with the most stupid thing, which is just take the vector space, which is the complex plane. Then you just have one operator to specify, and the ideal condition is trivial. So let's take this one, where we put just the coefficient A, B, C, D all equal to 1. In that case, a bit by definition, I mean FGN, if the A, B, C, D are all equal to 1, you would see that B is equal to 1, C is equal to 1. So you're just counting the number of terms. FGN is counting the number of terms that there is after you unfold the recursion in this formula. So this is counting a certain number of pairs of pen decomposition up to diffeomorphisms. But in that case, it's in fact easy to solve for the partition function. It's a second order differential equation. And after some change of variables, you can bring it in the form of the Airy differential equation. So you can compute what is exponential of f, and so get some formula for this number of pairs of pen decomposition. Now let's go to an example which is a bit more interesting, which is two-dimensional TQFTs. So this is a notion that was introduced by Atiyah in the early 80s. Here, you start to consider the category Borot 2, whose objects are compact 1D smooth-oriented manifolds, so a collection of circles. And morphisms are cobordism between these circles. So it's a surface whose boundary is a collection of circles, and you have an in boundary and an out boundary. On this category, you have a monoidal structure, which just means an operation which is associative, and here actually it's symmetric, is a disjoint union of surfaces of the circles. A 2D TQFT is just a representation of this category into something more elementary, like the category of vector spaces. And you want such a functor in such a way that it takes disjoint union to tensor product of vector spaces. So let's try to see what's inside this definition. So first, you have an object. So the simplest object is just the circle. You can apply the functor to it, you would get a vector space. So I call that V. Now, if you take a pair of pen that you see as a cobordism between two circles and one circle, this is a linear map from V tensor 2 to V. That's what the functor gives you. And using the fact that you can decompose cobordism, I mean, it is all symmetric, you can permute boundary and so on. And you can decompose cobordism in various ways. by the fact it's a functor, you realize that this product is commutative and associative. If you take the image by the functor of the cobordism between 2 circles and 0 circles, so this cylinder, you get a linear map from V tensor 2 to C. And using the axioms of, I mean, what is this bordism category? You get that this pairing, this is a pairing, so it don't degenerate. It's symmetric and it's compatible with the product in this sense. And then you get a unit, which is just by looking at the cobordism from an empty boundary to a circle. And that's a unit for the product. This collection of data, V with the product, with the pairing and unit satisfying all these axioms, is called the Frobenius algebra. The functor gives us much more because you can take any cobordism, not only those ones, and get some linear maps. But so there's a folklore theorem that was then written down carefully by Abrams, that it's actually there's a bijection between 2D TQFTs and Frobenius algebras. So we've seen one direction, how to get the Frobenius algebra from a TQFT, but just knowing the Frobenius algebra, you can get back to the TQFT. For that, so you need to compute what's F for an arbitrary cobordism. Let's assume for simplicity that you've put all your boundaries incoming and there's nothing outgoing. And take a pair of pen decomposition of the cobordism. Do it in any way you like. And then just define this to be, so for each pair of pens, so here you were going to put some element of V star tensor 3, which represents the product. Since you have a pairing in V, you can identify V and V stars, so you can convert some V into V stars. So the product, if I want, I can see it as a mu star, which is an element of V star tensor 3, which is actually symmetric. So I put a copy of this mu star for each pair of pens. And then each time I have to glue 2 pairs of pens together, I take the corresponding copy of V star, the corresponding copy of V star, and I apply the pairing on V star. In this way, what you obtain at the end, you just get a copy of V for each of the outer boundaries of this pair of pen, the one which are boundaries of the surface. So this is a linear map from V tensor N to C. And the Frobenius algebra axioms imply that this is not depending, this linear map is not depending on which pair of pen decomposition you chose. And actually this matches the TQFT axiom in the sense that this computes a TQFT, whose Frobenius algebra is the one that you started with. So the relation with Airy structure is the following. You can compute from the data of the Frobenius algebra these TQFT functors as the partition function of an Airy structure. So it would be an Airy structure on the Frobenius algebra itself, V. You have to put some A, B, C inside these differential operators. And you can take all of them, so they depend on 3 indices. So you can just take all of them to represent the product. Again, up to identification of V and V star. And then for D, well, you're going to take what the TQFT associate for the torus with 1 boundary. It's a linear map from V to C. If you do this, I'm claiming that the FGN that the Airy structure computes is up to this number of graph we already saw, is the TQFT functor. Why is that true? We come back to how the FGNs are defined from the Airy structure. So we see a sum. And as we saw, these terms correspond actually to removing pairs of pens. So I just prove it by induction. If the FGN minus 1 was coming from the TQFT functor, then I'm just putting the product, because here I chose B to be the product. And this is exactly what the TQFT rule is telling me. You have to take the value of the functor here and attach to that a product and do the pairing. So that's what this term is doing. But you also do it here and here. As I told you that the value you obtain doesn't depend on the pair of pent. When you write FGN in this way, you have a sum of all the pairs of pent that you can see when unfolding recursion, so all the pairs of pent decomposition. And then you, for each of these terms, you compose B's and C's and so on, which are just giving you the TQFT, the value of the TQFT. Therefore, what you will see, since the value, what you obtain doesn't depend on which term you look at, is the number of terms times the TQFT functor. And this is what is written here. Now, it turns out that, so we knew before how to compute the TQFT functors by these pairs of pent decomposition. But there are more interesting examples of Airy structures. But to see them, you have to go to infinite dimensional vector spaces. So I'm going to give definitions that are a bit ad hoc. You wouldn't see why it must be like this. I'm just saying that it works for the moment. And then maybe I will try to say a word, why does it work later? So take V, which is the space of formal series, which are odd in one variable Z. You can take a basis EK, which is Z to the 2K plus 1 or 2K plus 1. And I will need to define EK star, which somehow is the dual of this, which is rather a 1 form, which has a pole of order 2K plus 2 at Z equals 0. And now take theta, which is the inverse of a 1 form that starts with at most Z to the minus 2, and then higher order powers of Z. So then let's define A, B, C, D by these formulas, which look a bit like what we did in the Frobenius algebra. I understand that indeed A is some kind of product of three things, but now you have this residue and you're twisting by this theta. So EI, DI, DEJ, DEK are 1 forms. EI is a function, DEJ, DEK are 1 form. So this at the end is a 2 form and a bidifferential, a 2 form. You multiply by theta, which is the inverse of a 1 form. So this is the 1 form, you can take the residue. You select the coefficient of Z to the minus 1. And for B, it's a bit similar, except that somehow you replace EK by its dual, EK star. So these are some formulas, and you could say you compute and you check that this indeed forms a quadratic Airy structure. And if you allow to form linear combinations of the LIs, so maybe you're not in the right basis of V, you will see that it's based on the Lie algebra, which is isomorphic to a part of the Virasoro algebra. So these curly LIs are linear combination of the straight LIs. And they have commutation relation Li commute with Lj is I minus J, Li plus J. And so this is, you could say, a half of the Virasoro algebra. But depending on whether this theta minus 1 is 0 or not, you may push the half a bit further. So this turns out to be, in fact, very useful. So here are 2 examples. The first one comes from intersection theory on the moduli space of curves. So MGN is the moduli space of compact Riemann surfaces of genus G with some marked points, P1, Pn. This is a smooth orbifold of dimension, complex dimension 3G minus 3 plus n, but it's not compact. So it's hard to integrate anything on it. However, if you allow nodal curves which are stable in the sense that each smooth component, so you can attach smooth component at some nodes, and each smooth component should have negative order characteristic, so that there's actually a finite group of automorphisms. So this can be compactified. And then you can consider the cotangent line bundle of the curve. So a point in there is a Riemann surface with n points. You can take the cotangent space at the ith point. It's a complex line. And then when you vary the curve in the moduli space, this complex line is also varying. So this is forming a line bundle. And you can take the first Chern class of this line bundle, that's called the psi class. One part of Witten's conjecture in 91 can be reformulated by saying that if you take the Airy structure that I wrote here, take theta, which is z squared, d minus 2 times dz inverse, then the FGN are indeed the integral of psi classes up to some combinatorial factor. And in view of the relation, I mean, how you compute the FGNs from the Airy structure, the content here is that these psi class intersections satisfy Virasoro constraints, because we've seen this Virasoro algebra appearing. Here is another example, which this time is due to Mirzakhani, which existed again before Airy structures. So now you want to look at the moduli space of bordered Riemann surfaces. So you fix some boundary length. And on this moduli space, there's a nice volume form, which is called Weil-Petersen volume form. And the moduli space then has finite volume with respect to this volume form. One of the results of Mirzakhani is that you can compute these volumes as FGN obtained by the topological recursion. So these volumes turn out to be polynomials in the LIs. So here the coefficients I write FGN K1 Kn. And these are the coefficients of the partition function of the Airy structure I wrote before when you take this theta. Of course, at this stage, these two examples seem to come out of the blue. What I may say at the very end, if I have time, is an idea that actually all this is constructive. You have to guess nothing. You can prove this from geometry of surfaces. But I wanted to present these two simple examples to show you that indeed this algebraic gadget that we call Airy structures, then the FGN, they're interesting example where it computes something about surfaces. Okay. So once you have an Airy structure, you can do various operations on them, because you can let the Weil algebra act on itself by conjugation. That's an automorphism. And if you take automorphisms that are exponential of purely quadratic differential operators, it is acting trivially on the derivation on dρ dxi, but it's shifting xi by differential operators. So this preserves Airy structure. It preserves the form when you have an Li of this form, like this. If you change x into x plus something containing only differential operators, it doesn't spoil the form of these operators. They still start with a degree 1 condition. And because you're doing a conjugation, it doesn't spoil either the commutation relations. You just get an isomorphic Lie algebra. So in that way, you can generate many other Airy structures from a given one. there's another simple thing you can do is take two Airy structures on some vector space V and V prime, and then do a direct sum. This is still an Airy structure. But if after this direct sum you start to apply this conjugation, you can actually mix the two components in a non-trivial way. So you really generate a lot of Airy structures in this way with these two operations. In particular, the example I showed you based on this loop space, instead of looking at formal series valued in C, you can look at formal series valued in some Frobenius algebra. So you can couple the example, the TQFT example of Airy structure I showed you, coming from the Frobenius algebra, to the loop space example I showed you to make Airy structure based on that vector space here. So I'm saying that for the following reason.
I mean, looking at the number of your pages, you have about 10 minutes, so maybe you should. Yeah.
I will skip certain things. So what I want to say is that, in fact, you can reformulate these Airy structure constraints in terms of some singular property of certain differential forms. So let's define omega gn, which is some differential form. So this ek I star was dzi over zi to the 2ki plus 2. And let's put the fgn as a coefficient of this. The constraint to have an Airy structure, I mean, from the theorem I showed before, is equivalent to require that this combination of meromorphic forms actually has no poles, or at least has control singularity when z goes to 0. This is called abstract loop equations. And once you see this, you can generalize it to take any smooth complex curve with two functions x and y on it, and some symmetric bidifferential, so like dz1, dz2 over z1 minus z2 squared, and construct an Airy structure. So here I'm going to skip the details because I just want to convey this idea to see how to explain how it appears in matrix models. So from any curve with a branch cover, with some condition, you can attach an Airy structure, and therefore you have something computed by topological recursion. So now matrix models. Here we look at the probability measure on the space of Hermitian matrices of size n. And for simplicity, I'm just going to look at measures of this form, where V is some polynomial that's which is such that this measure has finite mass. Then you may be interested in the spectral invariance of this matrix, so trace of powers of the matrix that you can put into a single object with these cumulants. And ideally, you would like to compute these WNs, especially when the matrix becomes very large. There is a tool called Schwinger-Dyson equations, which consists in applying integration by parts to compute certain expectation value with respect to the measure. So for instance, I wrote here trace of 1 over x minus m squared minus trace of n v prime m over x minus m. This is a coboundary when you integrate in the measure, so you get 0. And this you can rewrite solely in terms of these WNs in this way, where on the right-hand side, this plus means the polynomial part of v prime x w1 of x. These are some functional relations. Here I wrote just the first one, but there's a whole tower of them for that involve wn plus 1 extra up to w1, and these for any n. And they are very useful when you want to understand how these WNs and how the matrix model behaves when n becomes very large. If you assume, so if you want to study the large n limit under quite weak conditions, so the matrix M has a spectral measure, which is just a Dirac with mass 1/n at each of the eigenvalue. And because the matrix is random, the eigenvalues are random, so you get a random spectral measure. In the larger limit, under good conditions on V, you can prove that these converge to some deterministic measure. So it's as if the most likely was that with high probability, macroscopically, the eigenvalues are distributed in a certain way. So this is measure lambda, and therefore, when you compute this expectation value of this trace, you get the Stelius transform of the measure. So this you can use to define a curve, which is called the spectral curve, which is essentially the curve on which the function, so W01 of x as a function of x, has a discontinuity exactly where the measure lambda has support, so where all the eigenvalues are condensing on the real line. But it turns out that this becomes, if you try to cross this, so x is going to be multi-valued, but it can be analytically continued on some Riemann surface. And you can obtain the equation of the Riemann surface by looking at the Schwinger-Dyson equation. The W2 drops out in the larger limit. You get an equation of the form W1 squared minus NV prime of x W1 equals some polynomial, which we don't know. It gives you an equation of this form. And then the main message, if I summarize works which appeared in the physics and in the math literature for over 20 years, the main message is that the WNs also have an expansion, a full or 1/n expansion, at least when the support of the measure is connected. It's in the form n to the 2 minus 2g minus n. And the WGN are defined, can be analytically continued on the same spectral curve. And now, if you take the Schwinger-Dyson equations, you insert the asymptotic expansion, and you play with it using analytic continuation on this curve, you're going to find that these Wn satisfy the abstract loop equations attached to the spectral curve, which I very briefly told you about before. Therefore, at least in this case where the support of the measure is connected, these omega GNs are computed by the topological recursion of that spectral curve. So that's the general idea. And this idea is working in a similar way for many more matrix models, not just this very simple measure, but you could have something like this with product of traces, or certain things also coming from colored tensor models. So there's been a lot of work that somehow extend what I just said to compute the expansion of these correlators by the topological recursion or some variant of it. So I guess now the time is about 5 minutes. Is it right?
Yeah, something like this, yeah.
In these 5 minutes, I want to explain that G and N are not artificial, but you can lift that to a theory that's really a construction about surfaces from the start, not from some algebraic gadget. So the idea is that you want to consider the category surf, where objects are bordered surfaces. And as morphisms now, you want to take isotopic class of orientation preserving diffeomorphisms. So like in TQFT, this category is too complicated. You want a representation of it. So let's assume that you have a functor from serve to some category of vector spaces. You have to impose some condition on this category to make what I'm going to say work, but I'm going to skip this. So what we mean by natural construction is called, more precisely, a functorial assignment valued in this functor. This is the data for each object, so each bounded surface of a certain element omega sigma in this vector space E sigma, in such a way that whenever you have a morphism between two surfaces, sigma and sigma prime, the functor gives you a linear map between the corresponding vector space, and you want that it sends omega sigma to omega sigma prime. In particular, you have automorphisms of the surface, which correspond to mapping classes, so isotopic class of differ of a given surface. And if you want this compatibility, that a fortiori means that omega sigma is mapping class group invariant. There is a theory called geometric recursion, which we developed with Anderson and Orentin, which constructs such functorial assignments by induction on the Euler characteristic. And I'm going to show you how it works on with one particular E, which is functions on the Teichmüller space. So the Teichmüller space can be described in many ways. One way is to say the set of hyperbolic metrics on sigma, such that the boundary is geodesic, and you want that up to local change of coordinates. Because you just divided by this diffeomorphism isotopic to the identity, you still have the action of this mapping class group, which is diffeomorphism of the surface modulo the one isotopic to the identity. And the quotient is something that we know, it's the moduli space of bordered surfaces. So let's take E sigma, which is functions on this Teichmüller space. You want to produce a function of a hyperbolic metric. And if we produce a functorial assignment valued in this, it means we actually produce functions which are invariant under the mapping class group, so it's functions on the moduli space. And to produce such a thing, I want to use this idea of removing pairs of pens as I did before in topological recursion. That's what we saw. But here in a much more concrete way, because you do have a surface. And the thing to do is to look at homotopy class of embedded pairs of pens inside the surface, satisfying all the conditions that I had before. So you have this set P sigma of homotopy class of pairs of pens, which are embedded so that when you remove, this is stable, and it's bounding the first boundary of the surface. This set is countably infinite. And if you divide by the mapping class group, you find back some other class, not of homotopy class, but diffeomorphism classes. And you are back with a set of terms of the topological recursion that we have seen at the beginning. So now instead of summing over all types of pairs of pens up to diffeomorphism, because I want to do something more geometric, I'm going to do it up to homotopy only. So we want to set up a recursion. For that, we have initial data that I still denote A, B, C, D. So A, B, C are attached to the pair of pens. So it's functions on Teichmüller surface of a pair of pens. And the hyperbolic metric of a pair of pens is just determined by the three boundary length. So it's a function of three variables. And D is a function on the Teichmüller space of the torus with one boundary. The construction consists in saying that for Euler characteristic -1, for omega p, you take the function A. For omega t, you take the function D. If the surface is disconnected, just take the product of the functions coming from the separated Teichmüller space. And so then you just need to specify what happens when you have a connected surface, which is not a pair of pens and not a torus. And for that, you say the following thing. You're going to sum over all ways of excising this homotopy class of pairs of pens. depending on which situation you are in, you put a B or C. And what's the value of this function on a given hyperbolic metric? The B you evaluate, the B and C you evaluate on the triple of hyperbolic length of these boundaries of the pair of pens. And the term omega sigma minus P that you already know from the induction process, it's a function on Teichmüller space of sigma minus P. You evaluate it on the restriction of the hyperbolic metric to sigma minus P. So this sum is countably infinite. The theorem that we proved on the standard Orantin is that if A, B, C, D satisfies some decay conditions, first, this is well defined. Then it's a functorial assignment. And this is just because the mapping class group just permutes term here within this sum. So as soon as you know it's absolutely convergence, you know that it's going to be mapping class group invariant and then actually a functorial assignment. And the relation on which I will conclude with the topological recursion is that let's integrate this function on the moduli space of Borot Riemann surfaces with fixed boundary length L. Now you just get a function of the boundary length. This is well defined under some conditions. And by design almost, it satisfies a topological recursion in the following form. You see the same type of terms as in the topological recursion, but now instead of having my Airy structure B, I, C, I, J, K, etc., I see operators whose integral kernels are the function B and C. So this is the key to prove in a geometric way both this Witten's conjecture in the form I presented before and this Mirzakhani recursion for Weil-Petersen volumes, because you just prove that the constant function 1 is given by geometric recursion. I will not detail this. In the hyperbolic case, that's a result of Mirzakhani. For the Kontsevich case, you have to do something a bit different, which is something that we do in a recent work with Anderson and a group of PhD students and postdocs in Bonn. But the idea is always express the constant function 1 from geometric recursion, integrate it. That implies topological recursion. And if you decompose what you obtain here on the basis of polynomials, you find back the coefficient of Airy structure that I explicited before. So my time is over. I'm leaving it here. Thank you very much for your attention.
Yeah, thank you for your talk. And so we can have questions. So maybe anybody who wants to ask can unmute himself and just ask, or maybe write something in the chat and then we can read it.